Hello everyone, I'm Yanping, and I want to share the paper named Simple Diffusion, End-to-End Diffusion for High-Resolution Images. Motivation: what is the problem with previous diffusion models? Diffusion models work well at low-medium resolutions, but training in pixel space at 512 or even 1024 becomes computationally expensive, numerically unstable, and poor in global structure. Prior work they do deal with this kind of issues, where latent diffusion, cascaded diffusion, or mixture of aspers denoisers for different resolutions. But these methods can strike because they improve the stability and cost, but also introduce engineering complexity. So in this paper, the authors believe the community has abandoned single-stage pixel space diffusion too quickly. They propose that with the right design choices, like noise schedule, capacity placement, regularization, and resolution pathway, a model can achieve just one model, one stage. Diffusion at the pixel space deal with high-resolution images, and it's just end-to-end. There is the intuition of this paper. They did these four things that the previous method did not. First, shifted Coulson noise schedule. Add more early noise so high-resolution models learn global structure stably. Concentrate model capacity at the 16 times 16 layer. Put most model width depths where global layout is formed for better coherence with low memory cost. Drop out only at low or mild resolutions. It regularizes global features without damaging high-resolution details. The last one is downsample first, upsample last. Do most computation in lower resolution space to save memory and improve stability. Here's the method. Step 0, base framework. Pixel space diffusion model. It has fold process, which adds Gaussian noise via a noise schedule. Also reverse process, which is a new net predicts V, epsilon, or X naught, depending on the method that we use. The loss is just standard diffusion objectives. As for the conditioning part, class conditional ImageNet generation and text conditional generation using a frozen T5 XXL with classifier-free guidance at inference. Step 1. Shifted and interpolated noise schedules. Start with Coulson log SNR, and then add the resolution-dependent shift, which is the delta D here. For example, the 64 times 64 shift is just 0. It makes high-resolution images much noisier at early time steps. As for the interpolation, it just makes the shift equals to 32 and shift equals 256 schedules to provide smoother frequency emphasis across scales. Step 2. Multi-scale diffusion loss. Compute noise prediction loss at full resolution and at downsampled resolutions, giving high weight to lower resolutions. It enforces correct global structure early in the reverse process. The third step is architecture, capacity concentrated at 16 layer. Keep the overall UNet shape mostly standard, but increase block count and width only at 16 times 16, where the global layout and object shapes are determined. It also includes the UVIT variant. Step 4. Downsampling at input and upsampling at output. There's two methods, wavelet and stranded convolution. Both approaches speed up training, reduce memory, and improve FID compared to no downsampling. Then the last step is dropout placement. The dropout only happens at 16 and 32 layer. It regularizes global features without damaging high-resolution details. And the result in the paper shows that they evaluated with no sampling streaks for fair comparison. And the simple diffusion outperforms prior single-stage pixel space models and even cascaded systems from 128 to 512, including approximately 4.3 FID at 512 times 512. It also achieves competitive text-to-image quality with ablations showing that each proposed component is necessary. Thank you.